Hi, I'm Ameya Tanikella, and this is my presentation on reinforcement learning in economics with a focus on central bank um, interest rates and stock trading. So the research questions that I've explored through this project are number one for the central bank. How can we determine monetary policy with reinforcement learning using artificial neural networks rather than Taylor's rule? And for stock trading, how can we use artificial neural networks similarly to predict stock market fluctuations and calculate appropriate trades? So to create my custom environments, um, I had some design questions and a process that I followed. So this would be the skill that the environment had to do, that the agent had to do, the information given to the agent, what actions the agent can take, success, and when the episodes should end for each session. So the skill for the central bank is to predict monetary policy, so the interest rate, and the information given are the interest rate, output gap, and inflation rate, and also the output gap from one time step before, the inflation rate from one time step before, and the interest rate from one time step before. And in this environment, the agent can choose between a random interest rate between 0 and 10, 0 so that it adheres to the lower 0 lower bound. The data that I used to start off the reinforcement learning environment, however, was data from 2025 quarter 2. And sorry, for the success of this model, there's a reward function that tells the agent whether it's doing a good job or not, and that is measured through this quadratic function. Because if it were not quadratic, then the reward could be too negative or too positive, and it wouldn't actually be calculating how good the agent was doing. So the closer the reward gets to 0, the better, because it is squared. So basically, that is omega times the inflation rate currently minus the goal inflation rate squared minus omega times the output gap squared. And omega is 0.5 for both. Omega is a measure of what the central bank wants to optimize the most, and the general assumption is that the central bank wants to optimize both the inflation rate and the output gap. So that's why we're giving equal weight to both factors. So omega will be 0.5 here. And when should the episodes end? The episodes should end when the time steps are completed. So I debated on ending the episodes when I reached a certain reward, but I found that that would just cut off the model and it wouldn't continue to train. Whereas if it trained when the time steps are completed, it gained a full sense of the environment and the complete picture. And now for the stock market. I did not use a custom environment for the stock market, but I used the Any Trading library from Python. But for the stock market, for the future, the skill that I would use is predict and trade stocks given an initial input of money. And the information would be stock owned, stock value on the date was bought, stock value on the previous day, capital for investment, stock value of last week, mean of stock values. And another thing that I was thinking of incorporating was like the general sentiment towards these stocks, because that can also affect them. And this could be measured through like social media websites and such. So that would be another component, but it would be definitely harder to implement. And for the agent, what actions can the agent in this environment take? It can buy stock, sell stock, or keep stock. And a more complex thing that I was thinking about was having multiple agents in this environment. It is something called multiple agent reinforcement learning, and that's because different agents act so differently in the stock market. So there are many different ways people trade and sell and buy. So these multiple agents would be representative of those different kinds of people. And I think that would paint a better picture of how the market would actually function, and it would help the multiple agents train in the environment better. And the reward can be measured through the price rate of change indicator. And so that's just another numerical metric that it should ideally be positive as opposed to 0 for the central bank. And it just basically shows how much the stock has increased over time. And when should episodes end? Again, when time steps are completed, because it allows the agent to stay in the environment for longer and thus gets better results. So now on to the research that I did for this project. So I went into this project without knowing much about reinforcement learning. I did know some linear algebra, which definitely helped, but in terms of reinforcement learning, it was a new topic for me. So for linear algebra, the most important concept in reinforcement learning is Markov chains. And Markov chains are is a model basically that describes how a system moves through a state. So basically in this example here, we have cloudy, rainy, and sunny. So see how the probabilities are just mapped directly to one another, showing how that they are only dependent on the previous action taken. So these probabilities are basically independent of one another. So you can see like sunny to cloudy, it's zero 0.1 every time. So when someone is at the sunny state, going to the cloudy state is always a 0.1 probability. So that's basically what a Markov chain is. And so the correct mathematical definition of the Markov chain is the Markov property. So basically, this means that the conditional probability of the current event happening given all the past events is equal to the conditional probability of the current event happening given only one past event. Basically showing that only the one past event matters. Like all of the others are basically useless. And this is important to reinforcement learning because that's how reinforcement learning functions, because it only depends on one prior state as opposed to many. But if in my model, for example, I do make use of multiple prior states and I do this, I work around this by actually putting it in my model's action space and observation space so that it still adheres to the Markov property. And this transition matrix here is a series of probabilities that is used to calculate the probability of an event happening for more complex things like reinforcement learning, and each of these rows will add up to 1. And the other equation that is really important for reinforcement learning is the Bellman equation. And so the Bellman equation in simple terms is just saying that the value of a state is equal to its current reward plus the expected value of the next state. So you can see here the Q value, that's the next value of the state, is equal to the current value of the state plus the reward, the maximum predicted reward, and minus all the possible actions. And this discount rate is typically 0.99 or 1. It just is a random function that is said to affect how much reward a reinforcement learning model could possibly have. And this is also illustrated through this equation here, which just maximizes the reward. So basically the Bellman equation just is the core principle of reinforcement learning, as the action that the agent takes is dependent on the current state of the environment, and so doing the reward function properly is a must in reinforcement learning. And now on to reinforcement learning basics. So what is reinforcement learning? So in simple terms, there is an agent and an environment. And this agent interacts with the environment and receives a reward based on the action it takes within the environment. So you can see with this part, the agent takes an action in the environment. It receives a reward, and the environment updates its state based on the action that the agent takes. So the environment is affected by the agent, and the agent's next action is affected by the environment. That is basically what reinforcement learning is. And there are two different kinds of reinforcement learning. Well, two main different kinds of reinforcement learning. So there's policy-based reinforcement learning and value-based reinforcement learning. So this kind of branches out into stochastic decision making and deterministic decision making. So stochastic decision making is that there's always a different action taken based on the distribution of time or the distribution of action. So based on the time steps that are completed, there's a different probability for each action that may happen. Whereas in deterministic decision making, no matter the state and no matter the time steps that are completed, each action has the same probability. And policy-based reinforcement learning is basically used when the action space is not discrete. So an action space is the range of all the actions that the agent can take within the environment. So this could be discrete or continuous. So for example, for interest rate, this would be continuous because interest rate can be anything from like 0 to 5 or whatever. But meanwhile, if it was like trading stocks or something, this would be discrete because there's just buy, sell, or keep. So policy-based reinforcement learning is like DDPG, which directly aims to learn a policy that can map a probabilities to certain actions. So this is used to predict future values. Whereas in value-based reinforcement learning, which is also called Q learning, you are merely learning about the environment rather than predicting future actions. And some policy-based reinforcement learning algorithms use the reinforce algorithm that updates based on the gradient of expected reward. So you can see here, this is the gradient of expected reward, and it's based on the current reward plus the expected future reward, while value-based reinforcement learning uses purely the Bellman equation. However, policy-based reinforcement algorithms like DDPG still use the Bellman equation but modified. So now environments in reinforcement learning. So environments in reinforcement learning are composed of basically three main things. So there's the init function to basically define all the variables and the action and observation space, which are extremely crucial to your environment, as I've said before, because the action space determines what how the agent will act, and the observation space will determine what the environment and the agent see, which influences future actions. And the step function next is where the core of everything happens. So basically this is where the agent actually performs an action, and then the environment gives a reward to the agent based on transition equation used to control the variables. So like in the central bank example, inflation and output gap are the variables that are being changed to the transition equations. And these transition equations aren't equations in a traditional sense, but they are basically weights and biases given by a neural network that are used to predict the future inflation and output gap based on the action that the agent has taken. And finally, we have the reset function, which returns the environment to its original state. And this is important because reinforcement learning is a Markov process, as I've said before, which means that it is crucial that it resets after each episode. And this equation, the Taylor equation, is what is typically used to calculate current interest rate based on a goal inflation rate. So basically, this would be the goal inflation rate, and this would be the current inflation rate, and this would be the current output gap minus the goal output gap. And the goal output gap tends to be 0, so it is omitted in my reward calculation. I just have y of t. And it also uses the current interest rate to calculate the future interest rate. And next, the DDPG algorithm that I used in my project is one that is called an action critic model. So DDPG is unique in that it's both policy based and value based. So DDPG learns both a policy and a Q function at the same time with the Bellman equation. And that's why I said it uses the Bellman equation to calculate reward and not the reinforcement algorithm, because it isn't technically policy based, but at the same time it can be used to predict future outputs. And DDPG is used over something like Q-learning because one, it uses a neural network, and two, it works with continuous action spaces like interest rate. And that means that it's basically differentiable. Since this action space is continuous, um, we can use the Bellman equation and a Jacobian to basically differentiate and calculate the reward. So even though we can't do Q-learning, we can still use the Bellman equation because the function is differentiable. So now on to my methods and process of making the environments and stock model. So first, for my central bank, for the data collection, I used the FRED API, so the Federal Reserve Economic Data API, to get past data regarding interest rates, inflation, and output gap. And I used a pandas data frame to visualize the data from 1985 to 2010. I was thinking of going all the way to 2020, but I didn't want to overfit my data because I wanted it to be able to predict current rates without knowing actual current rates. So now I will do a quick walkthrough of my code that I used for both the monetary policy here and the stock market. So first, this is the data collection. So to get the inflation data, there was no like monthly available inflation data or quarterly available inflation data on the FRED. So I used the GDP deflator and I got the percent change from each quarter, and then I multiplied it by 100 because I'm using the percents in 100 in like non-decimal values. And then for the output gap, I got the potential GDP. Well, this is the potential GDP, and this is the actual GDP. And then I just subtracted the real GDP minus the potential GDP, divided it by the potential GDP to calculate the percent difference, and then I multiplied it by 100 as well to keep it consistent with the inflation. And then to get the interest rate, I used the federal funds rate, and yeah, I just got that data from 1980 to 2010. And then I put this all into a data frame, so inflation, output gap, and interest. And just to make it consistent across, I resampled it with quarterly data. And if it was not quarterly data, if it was like monthly or something, it would do the mean of those months. And it would also draw up values that were NA. And yeah, it would plot the data. You can see here I printed out some of the values and then I graphed the data. And now we have our, these are just some import statements for scikit-learn to train the two transition equation models for the inflation rate and the output gap. So this is just some basic code that I use the basic scikit model for, and I trained it on an MLP regressor, and I made the activation hyperbolic tangent function. I also used the ReLU activation, but it kind of overfit the data, and I didn't want it to overfit the data because then it would be really bad at prediction in the future. And originally I used the LBFGS solver because that was the default, but then it wasn't converging, so I used the Atom solver instead. And this code does 1,000 iterations, and I just put a random state, and that is my model. But with this, I think the challenge was compiling my data. So basically, I needed a tensor that was 1,8 in shape, but I didn't realize that at first. As you can see with this code that is commented out, I only appended the current data and one past, but I realized I needed a lot more. So I appended, this is current output gap, current output gap 1 in the future, inflation rate 1 in the future, inflation rate 2 in the future, interest rate now 1 in the future, 2 in the future. So the reason that this X output doesn't have the output gap 2 in the future is because I used it in my y output. Because basically we are trying to predict this value, so it wouldn't make sense to have it in here when, like, yeah, this is what's being predicted, and these are the variables being used to predict this value. And now the same thing for inflation. Basically, you can see here that we don't have 2 in the future for inflation, and that is accurately represented here. And then I just returned these outputs, and I trained the data and got my 2 models. And these models will come in use for my reinforcement learning. And we can see here the data is somewhat accurate, because if it's too accurate, then it's getting overfit to the data, and that is not good. So it has a training accuracy of like 86% and a test accuracy of 78%. So this is pretty good test accuracy, because test accuracy is basically data that it hasn't seen before. So the fact that it can get it right about like 80% of the time means that it's doing a good job. And these are the weights and biases that I'm using for my transition equations in the next step. And yeah, these are just the iterations, and you can see that the loss function decreases over time, showing that the model is basically converging. And now for my environment, I use the Gymnasium library, and from Gymnasium I created my own environment. I called it Economy for some reason. And so my init function is really long, because that is where I essentially did everything. So here I set my max steps to 50. So in a part of an episode, it will do 50 steps of this function. So once 50 steps are done, it will consider itself done as training. I put it really low at first. I put it like at 12, but the model wasn't really learning anything and it wasn't converging, so I increased the number. And now these were my initial values for inflation and output gap, and I just used fed data and for both of these values. And for the output gap, I just used my fed data here to calculate it. Yeah, but I deleted that now. And now I have a goal for my inflation and output gap, and these are according to the Fed. So for inflation I put 2.0, and for the output gap I put 0. So now this is where the inflation rate is set. So this sets the current inflation rate to be something between 0 and 7. And I just chose 7 because it was like pretty random, but big enough that it could have a range of values and actually learn. Because if I set it too close to the goal value, it wouldn't actually be learning from the environment. And now I set limits for the range of values so that the model doesn't cheat the system, because what happens often in reinforcement learning models is that if you set the limits to be too high or too small, it will like cheat the system. Like in other reinforcement learning models, they often find workarounds that humans can't imagine. So I put pretty reasonable limits for these values so that it couldn't exceed a certain thing, because that would just be unrealistic. And now for my values, this is what I will be having in my state function. So we have current inflation, future inflation, current output gap, future output gap, current interest rate, and future interest rate. And so this sets a low for these values based on what I've set here, and a high. And now, so these are just what we are basically observing. And now I'm setting up the action space here. And the action space is the scope of the interest rate. So basically it defines what the interest rate can be. And so the action space is, you notice that it's -1 and 1. So that's not the value of the interest rate, but how much the interest rate can change each time. So originally I just had it set to a random value, and I found out that this was really random and the model wasn't converging. So instead I did it in smaller increments, that it would just be changing the current value, because that is how it currently works, because it depends, like the Taylor equation, it depends on the current interest rate to change. So I wanted to do something similar. And now I set my observation space. So we are observing the interest we're observing the inflation and the output gap. Two values of the inflation and two values of the output gap. And the shape of this is 4. And now finally onto the step function. So here what this function does is that it changes the value of the next interest rate, but it also clips the value so that if it goes lower than 0 or higher than 7, it will clip it to 0 or 7. And now we get the previous stored values, and this is legal because we've defined it in our observation space, so it is still Markovian. And then it tries to get a third value, and I just put this because here we don't have a third value at first, so I just made a quick workaround to that. And then it gets our previous values and then puts them into our transition equations. So you can see here it goes to the transition. So transition, it goes and plugs it into our model. It plugs all our values into the model, and then it spits out basically new values for the output gap and inflation based on the action that the agent has taken. And then it puts these values to the history and calculates the reward. As you can see here, we have omega, and we have our our inflation rate and our output gap. And basically what it does is if there's a particularly bad inflation rate such that it's deviating by 2, it will give an extra negative reward that will basically tell the agent that no, this is wrong, do better. And then I divide it by 10 to basically normalize it. And yeah, this function just resets everything and makes sure that the environment is going back to its original state. Finally, we have our DDPG algorithm. These are just some values that I experimented with. I had a pretty high learning rate. I had 0.01, and that just means how quickly the model retains information. But then I made it more low because I trained it on a lot of time steps anyway, so it was better that way. And so you can see here, it basically trains it. The mean is pretty low at -5. I think another time that I trained it, I had means at -1. But in this iteration, it trained to about -5 cumulative reward, which is pretty good. Now we can see here our values. So this value is basically the reward of the function, and -0.3 is a really good reward because we want our reward to be as close to 0 as possible. If we take a look here, we have our output gap is 0.27. Our interest rate is, our inflation rate is 2.8, and it's getting close to the actual values. And yeah, so now I visualize the data. I just use matplotlib to graph everything, and I graphed the inflation rate, output gap, and interest rate. I just graphed 5 episodes. You can see that this is very interesting. And I have more of the data later in my slides. And next, for the stock market thing. So here, first I got all my data from Yahoo Query, and I was originally going to do all of the S&P 500, but I didn't have enough time. So instead, this was for, I think I would expand on this on the future. So instead, I just plugged in tickers manually. So I had we can do Amazon or something this time. So yeah, it just generates the data. And this basically formats the data into something that can be plugged into the any trading environment. You can see your date, open, high, low, close, and volume. And basically what I did here was change the dates into actual date time, because before it was a string, because the any trading model would want the actual date time as an integer. And now we just have our environment. So I made it using the stocks environment, and the data frame was from before. And so here, window size is basically how many past points is it looking at, and the frame bound will start at this initial window size to approximately 2 less than the length of the data frame, so that it doesn't go out of range. And this one is just when I was testing it in random actions, and it did quite well for Celsius stock, but for Amazon it probably will not. Oh, oops, let me run this. Okay, there. Yeah, for Amazon the profit isn't as high. And I'm not going to train it again because it took 100,000 time steps and it takes quite a while, but this was for Celsius. It trained a lot and it got a profit of 1.63. So it sold it here when it was about, so it started here, it bought it here, and then it sold it finally at here. So it gained 1.63 times 100% in profit. So yeah, those were my two models. I tried it with a lot more stocks. I just plugged them in to the ticker here and got the data and tested it out. So now that I'm done with the code walkthrough, I wanted to just talk about like some of the processes of creation. I think I already talked about this, but like mistakes and errors that I made. So like the logic of reinforcement learning, because I wasn't very aware of the Markov process, which also connects to the math of the model. Like I kind of knew linear algebra, but I really didn't know it would be that hard. And with the parameters of all the variables, that was also hard to determine because the model would converge depending on certain factors, and finding those factors what required a lot of experimentation. And furthermore, for like the reward function, it's basically the same issue because at one point I was multiplying my reward by 10, which caused the model to go crazy. So I decided ultimately that I would need to divide my reward, so it taught the model to like actually try and converge to a value. And next, the interval for the values, so that also, because I didn't want it to do reward hacking, which is what reinforcement learning does a lot, and I think I mitigated that issue with my new intervals. So now on to some results. So first we have our central bank interest rate results here, and this is for inflation, this particular graph, and we can see that as the model learned, the inflation rate tended to around 2, except for this run. And so these values don't matter, it just represents where the model started, and this value here matters the most because it represents where the model ended up in the end. So it roughly converges to about 2%. So you can notice that this is 2 and that's 2.25. They're pretty close. Excluding the outlier, these two are very close to what the goal is, especially the green and the red graph, as they're almost nearly on the dot. So this graph does look a little bit crazy, but this represents the output gap. And the reason that it is so crazy is because the reinforcement learning agent takes a random action each time. And it's not really going from a very big numbers each time. It just looks like it's going crazy because the values are in a very small margin. We only have from 0 to -1 here. And again, the end matters the most. We can see here that we've achieved a good output gap. We have one at exactly 0 and the others are very near to 0. So yeah, that is the goal for the output gap. We want it to be 0 in our economy. So this accurately represents how the ideal economy would work. And finally, we have our interest rate results, which did not disappoint because although they started out in random places from 3 to 7 and had very interesting ways of converging, all of them ended up between 3 and 4. And this is actually really good because I believe the Fed's goal interest rate is 3.5%, which shows that even though the model was only had access to past data from like 2010, when it was given 2025 Q2 data and Q1 data, it was accurately able to find the goal and interest rate for this economy. And this is just a graph of the cumulative reward of the function. And so the reward is extremely low. Like, it does look like it's going to some big number, but that number is just -2. And this is the reward accumulated over 50 episodes, which means that each step only had like 0.01 reward, which is really good, showing how this model has fully converged. And now on to stocks. So first we have Meta, and the green dots represent buy and the red is sell. So we can see where it got sold and where it got bought, and the reward was 103%. And here's Nvidia. So this was a bad year for them. Their thing kind of tanked, but the model was still able to get a reward of 1.08 because, no, sorry, not reward, but a profit of 1.08. That's a decimal percent because it sold it early before it tanked. I mean, it could have sold it at here as well, but sometimes the model isn't able to accurately predict what will happen. So this is real data, by the way. And so this is 2023 to 2024. So this profit doesn't actually accurately represent what happened because it did not sell the stock, but assuming that it did, it bought the stock at 25 and now it was at 50 here, so it would have doubled its profit. So that would be a 200% profit. And finally, Celsius. So this one basically increased from 40 to 100, and that was accurately represented in how much profit the model made, so it was able to sell it here right when it was getting high, and it shows how the model actually made a profit from the stock, about 163%. So I have a lot of improvements that I want to do. So for the central bank model, I want to improve the reward function to be even better because it heavily depends on the ANNs to work right now, and I want it to work even when the transition equations aren't perfect. And I also maybe am thinking of collecting more recent data to use because that might predict rates even more accurately, but when we're trying to predict the future, we don't know too much, so I think leaving it at 2010 might have been good as well. Another thing is that I'd probably train it on more episodes. So train it around like 800 episodes and 25,000 time steps, which is a lot, but I think I could train it on even more to make it better. And finally, for the central bank one, I would include more real-world variables in the environment, and especially for the stocks one, there are a lot of ways I could include real-world variables that I am definitely planning on doing. And a big improvement that I would do for the stock model is use multi-agent reinforcement learning, also known as MARL. And that is because, as I've said earlier, that different people trade these in different ways, and by not simulating that, it doesn't accurately represent the environment. And that's kind of what I mean by introduce more real-world variables, and things like sentiment and all of that could also play a big role in how these stocks fluctuate. So using multi-agent reinforcement learning might actually accurately predict the model better than just simple data. And I would also like to train my stock model on custom artificial neural networks and a custom environment because I don't really like the any trading environment. I don't think it's accurate, but it doesn't really find the best thing to invest in. And so I would like train it on the entire market instead of just on one stock. So finally, the connection to economics. So The central bank interest rate model can basically be used to anticipate future interest rates. As we can see here, just by using data from 2010, we were able to anticipate inflation interest rates for 2025 and all of that. And this basically connects to economics because a lot of economics is just optimization of all these factors, and this is basically the main purpose of reinforcement learning. And that's why I chose this project in the first place, because I'd heard of reinforcement learning and I thought it was really cool. And I also didn't know how hard it would be, and I really found out that it was a challenge. And next, the stock market model can be used to predict and trade stocks. I think I can make it work at a higher level than it is currently, and this directly relates to the economy because financial assets are a component of Unit 4 and also economics in general. So these are my sources, and finally, I just like to say that this was really a fun project for me, and like just learning about all of this, I didn't know it would be this hard to do, and the project with the stocks that I have planned is definitely a little bit out of scope for me currently, but I will definitely work towards it in the future. Thank you for listening.